Hey everyone, and welcome to my channel. Today we're going to be taking a deep dive into the world of calculus. Specifically, we're going to be learning about the derivative of the cot function. Now, I know what you're thinking. Calculus can be pretty intimidating. But trust me, with a little bit of explanation and some cool visuals, we can break it down into something that's actually pretty easy to understand. So, let's imagine we have a circle with a radius of 1 unit. Now, draw a line from the center of the circle to a point on the circle. This line forms an angle of x radians with the horizontal axis. We can also see that the length of the vertical part of the line is sine x, and the length of the horizontal part is cosine x. Now, let's increase the angle by a tiny amount, dx. What happens to the vertical and horizontal parts of the line? Well, the vertical part will increase by cosine x times dx, and the horizontal part will decrease by sine x times dx. This is because as the angle gets bigger, the vertical part gets longer and the horizontal part gets shorter. But what about the cot function? The cot function is simply the ratio of the vertical part of the line to the horizontal part. So, cotangent x equals cosine x divided by sine x. Now, we can see how the change in angle, dx, affects the cot function. To understand this better, let's express the cot function in terms of sine and cosine components. We can also represent the cot function at angle x plus dx in the same way. The difference between these two expressions will give us the change in the cot function for a small change in angle dx. Before we continue, let's simplify the equation a bit. This will make it easier to see what's going on. We can do this by representing all the cot functions in terms of sine and cosine. This will also give us a better geometric understanding of what the change in the cot function looks like. The cot function tells us how many sine components can fit into the cos component. So, for angle x plus dx, the sine component increases and the cosine component decreases compared to when the angle was x. But to see exactly how much it changes is a bit tricky. This is because the change in length happens in both the numerator and the denominator of the cot function. To see the geometrical meaning more clearly, we can split the numerator of the equation. The first term represents the change in the cot function due to the change in only the denominator value, which is the change in the sine function. The second term represents the change due to the change in the cosine function. The first term reflects the change in the cot function due to a change in the denominator, sine function, alone. Red signifies sine x length, while blue represents additional length added, cosine x times dx. If we fill the cosine side with the same number of resized sine sides as when the angle was x, we get cos x divided by sine x. However, we notice that the covered length goes beyond cosine side. For each red part, there's a corresponding blue part, totaling cot x blue parts, each with a length of cos x times dx. This gives a total additional length going beyond cos x is cot x times cos x times dx. We have to remove this length, hence the negative sign. Using sine x plus cosine x times dx as the denominator introduces second-order terms in dx, which are negligible for small changes. So, we approximate the denominator as sine x, resulting in a change in the cot function due to the first term will be the original cot x value minus cot squared x. In the second term, we observe first-order changes in both the numerator and denominator, leading to second-order changes dx squared, which we want to avoid. By neglecting the cosine x times dx part in the denominator, we get a simplified value of 1 dx. Combining the simplified terms, we obtain cot x plus dx, with the isolated changes as cot x minus cot squared x times dx minus 1 dx. Removing the original cot x value leaves us with only the change d cot x, which simplifies to cosecant squared x times dx. Finally, taking the ratio of the functional change d cot x to the angular change dx gives the derivative of cosecant squared x. Now, let's explore the derivative of the cot inverse function. This function performs the opposite of the cot function, taking a cot value x as input and returning the corresponding angle theta. We can derive the cot inverse function's derivative using the derivative of the cot function. Here's the process. The first step is to replace x with theta. Since the angle isn't the independent variable here, we follow notational conventions and use theta to represent it. This allows us to express the derivative of cot in terms of theta. The second step is to treat cot theta as the independent variable x. We substitute all terms with x because we need the equation in terms of the independent variable. By following these steps, we obtain the derivative of the cot inverse function. And there we have it. We've journeyed through the fascinating derivatives of the cot and its inverse, hopefully making these concepts a bit more clear. If you enjoyed this exploration, please leave a like and subscribe for more intriguing math and physics content. Don't forget to share this video with others who crave learning adventures. Happy exploring, and until next time.